We have some rules associated with Kirchoff's rules so we can solve the problems. Don't worry if all this doesn't make sense to you just now. Once we work the problem, hopefully it'll become clear. And if you do get confused later on, you can always refer back to this slide and the next one. So the first thing you do for each circuit element, draw an expected direction of the current. You don't have to worry about this too much. If you choose the wrong direction, after you get done with all the algebra, you'll get a negative value for the current that you chose, which means it goes in the opposite direction. Not a big deal. Label each resistor with a positive or a negative sign. And here's how you do that. And this is critical. You have to do this. You don't have a choice. The positive sign is where the drawn current enters the resistor. The negative sign clearly would be the other side of the resistor. Then for every junction you have, apply the junction rule. You'll need as many equations as there are unknowns. So a lot depends on what problem statement you have, how many givens you have, and what you have to find. You can also use Ohm's law to reduce the number of unknowns. For example, if at a resistor they tell you the resistance value and the current, well, you can go ahead and find the voltage right there without even using Kirchoff's rules. Okay, on to the next slide for some more rules. You apply the loop rule for each loop that you have. You draw a loop, and then you sum up the voltages in the loop to equal 0. The convention there is as we're traversing the loop, here we go, we chose one in the clockwise direction. If you enter the positive side of a resistor, remember we did that in the last step, then you assign a negative sign to the voltage. If we were going in the counterclockwise direction, we would be entering the negative side of the resistor, and you'd apply a positive sign to the voltage. The battery V is positive if you leave the positive terminal with the loop. So if we're drawing this in a clockwise fashion, V will be positive. If we chose the loop to go in the other direction, V would be negative. So for this one, where we're going in the clockwise direction, we have a positive V, minus V1, minus V2. We then use Ohm's law to substitute for V, and we get V minus I1R1 minus I2R2 equals 0. And then we'll have a set of simultaneous equations with the junction rules and the loop rules. And then you solve them. And that takes practice. And we'll do a practice example coming up next. Let's apply Kirchoff's rules to this circuit. We're given a resistance here, given a current, a resistance here, a voltage here, and we want to find everything that we don't have. For example, we're going to want to find V1, and we're also going to want to find I1 for this resistor. Now, if you look at this circuit, we really don't need Kirchoff's rules, but I didn't want to start with something very, very hard that would be too tough to follow. If we were just using Ohm's law, we turn these two resistors into one resistor. They're in series. This equivalent resistor would then be in parallel with this one, so we could replace that, and then we'd have two series resistors, add them together, and we get the equivalent resistance. But we're going to go through Kirchoff's rules here. How would we not be able to just use Ohm's law? Well, what if we put a battery over here? That would throw it off. Then we would have to use Kirchoff's rules, and we're probably going to save that for AP2. Step 1. Draw an expected direction of the current for each circuit element. And you may recognize this. We took this off our list of rules from a few slides back. Direction doesn't matter. If it turns out the real direction is in the opposite direction, you'll get a negative value for the current. So here's the battery. Notice that this is I2 going through resistor 2. It comes down here, so the current going through the battery is also I2. We then come this way. We say the current's going to go through here, through here, through here. And then we're making the assumption the current comes this way through R4. Let's see if that holds up. We don't care right now. We'll work the algebra and see what answer we get. Now this step you have no freedom on. If you've already drawn the current, which we have in step 1, we have to label each resistor with a positive and a minus sign. The positive sign has to be where the current enters the resistor. So there's a positive, there's a positive. Then for this one, this would be a positive for resistor 4. And here is resistor 2. And then, of course, you will have negatives on the other side of the resistor. So far, so good. Next, apply the junction rule. How many junctions do we have in this circuit? That's where 3 or more lines meet. Well, we have junction 1 up here, and we have junction 2 right here. So for junction 1, we have I1 coming in, and then I2 and I4 coming out. So I1 equals I2 plus I4. At junction 2, we have I2 coming in, we also have I4 coming in, and I3 coming out. So I2 plus I4 equals I3. Again, not too tricky just yet. Now we apply the loop rule. And now it gets a little busy, but let's just follow this. We're going to choose 2 loops. One here in a clockwise direction, and the second one here. Can you see a third loop that we could have chosen? Well, look at this. If we start at the battery, goes here through resistor 3, resistor 1, and then keep going. Resistor 2, and all the way down back. That's also a loop we could have chosen. Turns out in this case we won't need it, but that you could have done that also, chosen the big loop around. You're not limited to the little loops. So let's look at loop 1. What do we have? Well, there's no battery in loop 1, so let's start here. We're going clockwise, so as we enter this resistor, we're entering at the positive end, okay? So that means we have a negative voltage, so you can see the negative V3. We come up here, same thing with resistor 1, entering the positive, so it's a negative V1. Come down to I4, entering the positive side of the resistor, negative V4. We then put in Ohm's law, and we have our equation for loop 1. Now let's look at loop 2. We start at the battery. We're going across the battery clockwise, and we're leaving the positive terminal, so that is a plus V. Now, look at resistor 4. We're entering at the negative side, so we're going to give that a positive V4. We keep coming up here. Now we're entering the positive side of this resistor, so that gets a negative voltage. So now we have our 2 loop equations. And again, let's just talk about what would happen if we took the bigger loop. You would have V minus V3 minus V1 minus V2 equals 0. Also perfectly good. This slide looks a little busy, but relax. We're going to take each little piece, one piece at a time, and hopefully it'll make some sense. We start with the junction 1, where you had I1 is equal to I2 plus I4. We look at our givens. Hey, there's I2, it's 2.6. We just plug it in. Same thing for junction 2. We have I2, we replace it with 2.6. Loop 1, here's the voltages, here's V equals IR, and let's see what we can plug in here. Let's see, I3, R3. Where is that? That's over here. We don't have I or R, but we do have the voltage, 1.7. So we'll just put that in over here, 1.7. I1, R1. R1 is 5, so that's 5I1. And then let's look at I4. We have the resistance 2. You put that in for R4, and you have 2I4. So now we have 3 equations. Loop 2. What do we have for loop 2? Let's see, the voltage of the battery is 12. There's 12. The resistance for I4 is 2. And then look at this, I2, R2. We weren't given voltage, however, we were given I2 and R2. So to find voltage, that's Ohm's law, 2.6 times 3, 7.8. So we now have 4 equations that have all our givens in them. Hopefully things are starting to look a little more clear now. We've rewritten our 4 equations, and now we're going to put them all together without all of the stuff that came before. And we're going to look at these and see what we can do with it. And this is where your practice and insight comes in. The more problems like this you do, the easier it gets. Let's look at equation L2, the loop 2 equation. What do we have? We have a number, we have 2I4, and we have another number. What can we do? Well, we can solve for I4. And it turns out that I4 is negative 2.1 amps. What does that negative sign mean? Well, it means we chose the direction of the current backwards. I4 actually goes in that direction. Not a problem. We now have I4, and let's look at loop 1 equation. It has I1 and I4. I just plug in that value for I4, and I find that I1 is 0.5 amps. And we chose the right direction for that because we got a positive number. Okay, now we want to use equation J2. What is that giving us? Well, we now have I4, we have 2.6, we can find I3. I3 is 0.5 amps. Probably should have shown this earlier, but frankly I wanted to see if you came up with a way of keeping track of all the various currents and voltages and resistances. One way is to just mark them right on the circuit diagram. Another great way is to have a table. So the red numbers here is what we were given, and the blue will be the numbers we find. Well, we found the current from the last slide, so we put all the currents in here. Now, do we need Kirchoff anymore? Not really. As long as you have two of the variables, well, in this case we have all three, you can find the third just by using Ohm's law. So for example, the voltage across R1 would be current times resistance, or 2.5 volts. So let's move on to the next slide to see the answers. And here we have the results. Now would be an excellent time to go back to the original problem and try and solve it without following through the slides. Here's a problem you can try on your own. You can either go right to Kirchoff's rules, but I'll give you a little hint. You really don't need it. You just need some circuit knowledge, what happens to the current, what happens to the voltage, and Ohm's law. But you can do it either way. And one way to do it is if you're working it here, you can find a variable and you can pull out the box to see what the answer is. This one's pretty straightforward, right? If you have two variables, you can always find the third. V is IR, so this should be 20 volts, right? So see, you can pull that out and look at it. And as you go around solving everything, you can check your answers. Here's the problem all worked out. And by looking at the numbers, you can kind of make sure that you did the right thing. For example, here you have a 20 volt drop, here you have 30. So you lose 50 volts going this way. When you came here, this is in parallel, so notice that these voltages are the same. That's very good. They should be. They're in parallel. And if I were to replace these with one resistor, I come out of the battery, I lose 70 volts, then I lose 20, then I lose 30. When you add those together, you get 120 volts. So that's conservation of energy. And I'm being a little flip with the term lose. You're not losing energy. You're transferring the energy from one form to another. So this is the answer. Hopefully you got it.